Automatic Detection and Repair of Errors in Data Structures by Brian Dembski and Martin Renard. Abstract. We present a system that accepts a specification of key data structure consistency constraints, then dynamically detects and repairs violations of these constraints, enabling the program to continue to execute productively even in the face of otherwise crippling errors. Our experience using our system indicates that the specifications are relatively easy to develop once one understands the data structures. Furthermore, for our set of benchmark applications, our system can effectively repair inconsistent data structures and enable the program to continue to operate successfully. Introduction. To correctly represent the information that a program manipulates, its data structures must satisfy key consistency constraints. If a software error or some other anomaly causes the data structures to become inconsistent, the basic assumptions under which the software was developed no longer hold. In this case, the software typically behaves in an unpredictable manner and may even fail catastrophically. This paper presents a new approach for attacking the data structure consistency problem. Instead of attempting to increase the reliability of the code that manipulates the data structures, our system accepts a specification of key data structure consistency constraints. It then dynamically detects and repairs data structures that violate these constraints. Our goal is not necessarily to restore the data structures to the state in which a hypothetical, correct program would have left them, although in some cases our system may do this. Our goal is instead to deliver repair data structures that satisfy the basic consistency assumptions of the program, enabling the program to continue to operate successfully within its designed operating envelope. 1.1 Intended Scope. This research places a high priority on continuing to execute the program even after concrete evidence that the execution has sustained at least one error. We recognize that this approach is clearly not appropriate for all computations. In many cases, the best response is simply to stop the execution and await external intervention, or reboot the system and restart from a clean state. In some cases, however, continued execution is crucial. Our society is starting to deploy increasing numbers of safety-critical systems that interact directly with the physical world. Moreover, many of these systems rely completely on the active participation of the software for their continued safe execution, even if the only goal of that execution is to bring the system down safely so that it can be repaired. Embedded software often controls physical systems that enable Embedded software often controls physical systems that operate for significant periods of time in active or unstable states. If the software fails, the resulting uncontrolled operation can cause catastrophic damage that seriously threatens human lives and property. In this context, even a partially impaired execution is far preferable to no execution at all. Another broad class of systems monitors ongoing physical or information processes and presents summarized results to human users. The data structures in these systems typically reflect a sliding window of observations and predictions centered around the current time. Most data structure properties are transient, sliding through the system as it continually rebuilds its data structures to reflect its ongoing movement through time. In this context, any data structure anomalies will eventually be flushed out of the system as long as it continues to operate. Automatic data structure repair is one mechanism that can enhance the ability of those systems to execute through errors and eventually move back to a completely correct execution. Another rationale for continuing to execute is that the data structure corruption and repair may only affect a small part of the data and generated results in the system, with the other data and results still valid and useful as long as the program continues to execute. This is the case in our air traffic control application. Finally, many systems have persistent data structures, for example, file systems, application data files, or serialized data structures, whose inconsistencies persist across system restarts. By restoring key consistency properties, automatic data structure repair may enable tools or applications to work with or extract information from partially corrupted versions of these data structures. (1.2) The basic technical approach. Our approach involves two data structure views: a concrete view at the level of the bits in memory and an abstract view at the level of relations between abstract objects. The abstract view facilitates both the specification of higher-level data structure constraints, especially constraints involving linked data structures, and the reasoning required to repair any inconsistencies. Each specification contains a set of model definition rules and a set of consistency constraints. Given these rules and constraints, our tool automatically generates algorithms that build the model, inspect the model and the data structures to find violations of the constraints and repair any violations. The repair algorithm operates as follows. Inconsistency detection. It evaluates the constraints in the context of the current data structures to find consistency violations. Disjunctive normal form. It converts each violated constraint into disjunctive normal form, i.e., a disjunction of conjunctions of basic propositions. Each basic proposition has a repair action that will make the proposition true. For the constraint to hold, all of the basic propositions and at least one of the conjunctions must hold. Repair. The algorithm repeatedly selects a violated constraint, chooses one of the conjunctions in that constraint's normal form, then applies repair actions to all of the basic propositions in that conjunction that are false. A repair cost heuristic biases the system toward choosing the repairs that perturb the existing data structures the least. Note that the repair actions for one constraint may cause another constraint to become violated. To ensure that the repair process terminates, we pre-analyze the set of constraints to ensure the absence of cyclic repair chains that may result in infinite repair loops. If a specification contains cyclic repair chains, the tool attempts to prune conjunctions to eliminate the cycles. 1.3 Invoking Check and Repair. Our implemented system supports several mechanisms for invoking the consistency check and repair algorithm. One issue is that many correct data structure updates temporarily violate the consistency properties, then restore the properties as they complete. We must ensure that the check and repair does not interfere with such correct updates. Our first mechanism is to simply enable the programmer to identify points in the program where he or she expects the data structures to be consistent. At each such point, the repair algorithm executes to find and repair any inconsistencies. An alternate mechanism augments the program to catch signals from faults, such as divide by zero and segmentation fault violations. Because such faults are often caused by inconsistent data structures, the signal handler invokes the check and repair algorithm, then resumes the execution at the nearest consistency point. It is of course possible to use both of these mechanisms in the same program. For persistent data structures, we generate a standalone version that reads in the data structure from persistent storage, repairs any consistency violations, then writes the data structure back out. This version can execute independently of other applications that access the data structure, or it can be integrated with these applications to perform the check and repair immediately after a data structure is written out, or immediately before it is read back in. Experience 1.4. We have used our tool to repair inconsistencies in 4 applications. An air traffic control system. This system is in daily use in air traffic control centers surrounding several major metropolitan airports. A simplified Linux file system, an interactive game, and Microsoft Word files. In this context, we have applied the tool to correct out-of-bounds array indices, repair bitmaps identifying free and allocated disk blocks, correct reference counts, eliminate inappropriate sharing in linked data structures, correct illegal values stored in arrays, resolve inconsistencies in correlated values stored in different data structures, and ensure the correctness of recorded data structure sizes. Our tool is also able to correct corrupted pointers in linked data structures, repair incomplete data structures by allocating and linking in new structures, repair backlinks, such as parent pointers in trees, in linked data structures, and enforce inequality constraints between multiple values. We found that the specifications for our applications are very small in comparison with the size of the application, and were relatively straightforward to develop once we understood the underlying data structures. We also found that the automatically generated repair algorithms were able to produce data structures that enabled the corresponding programs to continue to operate successfully. In the absence of this repair, the programs usually failed. Our results therefore indicate that our technique may significantly enhance the ability of applications to recover from data structure errors. (1.5) Other applications of our specifications. We have presented our approach as valuable because of its ability to enable programs to recover and execute through errors, even though the execution may not correspond directly to the execution of a fully correct program. However, there are other advantages that developers may find useful. First, developers may find the consistency checking functionality of our tool useful in its own right as a debugging aid to quickly find any inconsistencies generated by an incorrect program. For some deployed applications, the correct behavior is not to attempt to repair data structures inconsistencies and continue to execute, but instead to terminate or suspend as soon as an error is detected. Our consistency checker can be used to implement this fail-stop behavior. As soon as it detects a data structure inconsistency, it can be configured to terminate or suspend the execution. Second, our consistency checking and repair functionality can be used to provide insight into the behavior of the program. It can be configured to produce a trace of the inconsistencies it found and repair actions it took to eliminate the inconsistencies. The resulting logs may help developers identify errors and help narrow down the source of the errors of the program. Finally, specifications of key data structure properties can also be useful as documentation or as a precise means of communicating the desired properties within or between teams developing the software. (1.6) Contributions. This paper makes the following contributions. Point. Specification-based approach. It introduces the concept of using specifications for the automatic detection and repair of inconsistent data structures. It also introduces the concept of using an abstract model of the data structures to facilitate specification development and reasoning in the repair algorithm. Point. Specification language. It presents a new specification language that enables the developer to express key consistency properties of low-level, highly efficient data structures in a clean, general way. Point. Inconsistency detection and repair system. It presents an implemented system and algorithms that, given a specification, automatically detect and repair violations of the specification. Point. Experience. It presents our experience using our tool for several applications. This experience indicates that it is relatively straightforward to develop the consistency conditions that the use of our tool enhanced the ability of the applications to continue to operate in the face of errors. The remainder of the paper is structured as follows. Section 2 presents an example that we use to illustrate our approach. Section 3 presents the specification language used to express the consistency constraints. Section 4 presents the inconsistency detection and repair algorithms. Section 5 presents our experience using automatic data structure repair in several benchmark applications. Section 6 discusses related work. We conclude in Section 7.